Okay, so this is the first of our divisibility test videos. You've probably, if you're watching this, probably do contest math, and probably you've already seen or been told, or you know that a positive integer is divisible by 3 if and only if the sum of its digits is divisible by 3. And the same thing is true for 9. We'll do a separate one with 9. You check that a number is divisible by 9 by adding the sum of the digits. If that's a multiple of 9, then so is the number, and if not, it isn't. The purpose of this is to basically, if you haven't seen a proof of this, the proof is going to use modular arithmetic. I'm getting ahead of myself here. Modular arithmetic. And if you've seen, if you've worked with modular arithmetic before, if you're familiar with it and all happy and comfortable with that, then this is going to be a very sort of simple, underwhelming proof. If you haven't, then the proof isn't going to make any sense. So, and again, I'm assuming most people are here for contest math. Modular arithmetic is absolutely crucial to contest math. So if you haven't done it before, if you have any hesitation about any of the stuff we do in this video, please check out the playlist on modular arithmetic, and then you can learn everything you need to know about that and practice it. And then a whole world of contest stuff will open up to you, and also number theory in general, and then you'll be able to understand the proof. So first, let's write, so n is our positive integer. We'll write n is equal to ak minus 1, all the way through a1, a0, and this is our base 10 representation of n. And again, I'm assuming that people doing contests have seen base 10 representations. If that's strange to you, then of course, please do check out the videos on that, where we just see how we write the standard way of the sort of notation for writing a base 10 positive integer. Of course, this is a sub k, so the leading coefficient, which is, or the digit actually here is what we would call it. That one can't be 0. This is ak times 10 to the k. We have all of the ai's in 0 through 9, with ak is not equal to 0, or else it wouldn't be a k plus 1 digit number. By the way, this is k plus 1 digits. We notice that the k here is the last, so ak is the leading digit here, and then we started counting at 0, so it's actually a k plus 1 digit number. So we have ak times 10 to the k plus ak minus 1 times 10 to the k minus 1, all the way through a1 times 10 to the 1 plus a0 times 10 to the 0. And that's the units digit, of course, the a0. So let me just put the coefficients, or the digits here in green. The units digit is being multiplied by 10 to the 0, which is just 1. So that makes sense. That is all good. And the subscripts line up, right? The subscripts match the powers of 10. Okay. And so the claim is that this is going to be, we want to show that n is congruent to ak plus ak minus 1 plus all the way through a1 plus a0 mod 3. And that means that they, I didn't mean to move that. Let's maybe just move this over a teensy. There we go. Okay, fine. I guess I have to move the whole thing over. N is congruent to the sum of its digits, mod 3. That means they leave the same remainder when they divide by 3. That means that they have the same remainder when they divide by 3. So in particular, if this is 0 mod 3, and that actually includes, in general, the possibility there could be 0 with some of the other divisibility tests, the higher level ones, or the ones for larger numbers, we're going to see that that's a possibility. Here we're adding the digits, and they're all in 0 through 9, and ak can't be 0, so it's not going to be 0, but that's always a possibility. For divisibility tests, people have a tendency to forget. They'll say, oh, this is equal to 0. That's not a multiple of 7 or something, but it actually is. It's 7 times 0. So okay, we're going to show this. How are we going to show that? Well, we're going to note that 10 is congruent to 1 modulo 3. Why is that? Well, 10 is 3 times 3 plus 1. It is a multiple of 3 plus 1. So it leaves a remainder of 1 when we divide by 3. And then, of course, that means so it's 1 mod 3. So 10 to the m is congruent to 1 to the m mod 3, and 1 to the m is 1 mod 3. So, and this is using the rules of modular arithmetic. So again, if any of this stuff is strange, please do check out the pretty lengthy playlist on modular arithmetic, where we go through the rules and we prove everything and we do a bunch of problems and show really cool applications. And this is one of them. Okay, so what does this mean? this means that, so we started with this first line. We had n is congruent to ak times 10 to the k plus ak minus 1 times 10 to the k minus 1, all the way through a1 times 10 to the 1 plus a0 times 10 to the 0 mod 3. So, and because this is just another way of writing n, right? This is literally what n is. It's that. And now we've shown that each of those powers of 10 is 1 mod 3, so we can replace them with 1 in here. Again, according to the rules of modular arithmetic, this is ak times 1 plus ak minus 1 times 1 all the way through a1 times 1 plus a0 times 1 mod 3. So, and of course, the next step is that all of these, anything times 1 is just itself, so these are all this is going to wind up being congruent to the sum ak plus ak minus 1 way through a1 plus a0 mod 3. And this is exactly what we were trying to show. This is the sum of the digits. Right? This is saying that n, this base 10 number, leaves the same remainder as the sum of its digits mod 3. As an example, let's just do something like say 1, 1, 1. This is 111. The sum of the digits is 1 plus 1 plus 1, which is 3, which is congruent to 0 mod 3, of course. And indeed, 111 is 99 plus 12, which is 3 times 33, plus 4, which is 3 times 37. So success. We were able to just construct, and you can do this, you can construct numbers which are multiples of 3 really easily, just by making sure that the digits add up to a multiple of 3. And if you get a number, like if I pick a random number, say like 3, 2, 7, 9, 1, well, let me look at the sum of the digits. This is, and first of all, you can just ignore the ones that are multiples of 3. So these are 0 mod 3, and then 2 and 7 is 0 mod 3, it's 9, and then we have a 1 left over. So this is not divisible by 3. This is not divisible by 3. We can know that just instantly by looking at this thing. So very nice test for divisibility by 3. There's also divisibility by 9. Divisibility by 9, I think that I said at the beginning I had to make a separate video for this, but as I'm doing it, the teacher in me is just screaming, leave this as an exercise, because it's very similar. So let's say, as an exercise, can you figure out what, you've probably seen this before, it's the sum of the digits as well, but can you prove the same thing for 9? Prove this, that, and it's the exact same thing, that n is congruent to ak plus I almost wrote in the tens, ak minus 1 all the way through a1 plus a0 mod 9. So the exact same divisibility test. If the sum of the digits are divisible by 9, then the number will be divisible by 9. So that's a great exercise to see if you can prove that. In the next videos, we'll check out the divisibility tests for 7. So I think we'll do 11, even though that one's, again, these ones are sort of just like an introduction to the idea that we can prove them. Very similar thing for 11. It's the alternating sum, so it's a different rule, but similar way of proving it. 9 is virtually identical. 5 and 2, those ones are fairly straightforward. We'll talk about those as well. But the real sort of thing is going to come when we start doing divisibility by 7, 13, 17, 19. Those are going to be the tricky ones. Those are the ones that historically my students always had trouble remembering those more than these ones. People always remember the 3, 9, 11, 5, and 2. And then 7, 17, 13, 19. Those ones are sort of tricky. People are always like, wait, what do I add? What do I subtract? So, and we're going to see that actually proving those and seeing how to prove them, this is the way we remember things in math. This is the way that we level up. We become fantastically good at math by better than we thought we could be by proving and understanding things. And then we also, you look like a genius when you know a million things, when you just pull something out of your brain and write it on a chalkboard or on a test. And it seems like you're a savant and you remembered so many things, but actually you just learned how to understand them. You put in the work and the effort and learned how to understand these things. So we are going to see that. We're going to learn how to have math superpowers with divisibility tests in the upcoming videos.